And let's start. Today we will be talking about support vector machine, and as you can see, it's an adaptation of a presentation made by Andrew Moore at the Carnegie Mellon University. I chose this presentation because I found it to be interesting and easy to understand. And therefore I follow this presentation in our course every year. So let's see. If you remember, we considered to be a linear classifier, a function that received some input vector x, and it computed the sign of wx plus b, where w and b are the parameters that need to be evaluated by the system to be learned from the dataset, from the training dataset. W are the weights and b is the bias. Based on the sign of this summation, the point is denoted as being part of one class or the other. So the input is an input vector x, and the estimation is a class that the classifier would output. And most of this lecture we will be talking only about classifiers with only two classes, and we'll denote them +1 and -1. Okay, just like we did at the perceptron. If you remember, we said that when we talked about perceptron, I told you that SVM is nothing but a smarter perceptron, and therefore we will be using the same notation, +1 and -1, and we'll go through the steps that help us identify the values of W and B based on the data that we have for training. So let's see. If we have this data set that is depicted in the center picture, the question is how to classify this data. Is the data linearly classifiable or not? Are you still here?
Yes, it is linearly.
It is linearly classifiable, okay? And now we have multiple options. So we might have a linear classifier like this, or another one like this, or another one like this. So basically we have a lot of such classifiers. And the question is, which one of these is the best classifier? What do you think? All of these classifiers would classify correctly all the data, okay? So first of all, let's establish that all of these are correct classifiers that will correctly classify the data. The question is, are all of them of the same quality, or some of them are better than the others? And if some of them are better than the others, which one of these is the best? What do you think? Any idea? Okay. Well, not all these classifiers are as qualitative as the others, because you can see. Let's assume that we consider this classifier. This classifier is extremely close to both positive and negative values. So you don't know, this is what you have in the training data, but you don't know what you might have in the test data. So you might have something like a point from here, and instead of being classified as +1, this classifier will classify it as -1. The same is valid for this one, which is close to a lot of negative points and also a lot of positive points. So basically, we don't want this one, we don't want this one. We would like to have a classifier. Let's suppose that this one would be that is somehow farther away to both positive and negative points. So in order to find this classifier, first we define the margin of a linear classifier as the width of the boundary that could be increased before hitting a data point. So let's suppose we have the classifier that we have in here. How much can we extend the area around the classifier in both directions before hitting some data points? For example, before hitting these 2 points or this point. And this is called the margin. And this is represented by the yellow area from here. Okay? Now, the maximum margin linear classifier is a linear classifier that have the maximum margin. And this is called SVM or linear SVM. And this one actually is the best classifier that we may get. So, as I told you, we would like to have a classifier that is somehow distant enough from any point, both from positive and negative sides. And this distance is defined by this margin. That is the distance that the classifier can be extended before hitting a data point. And again, this is an SVM, linear SVM. So the purpose is to find the maximum margin separator to have along with the following optimization problem. We would like to have Wx plus b greater than +1 for positive cases, and Wx plus b to be smaller than -1 for negative cases. Also, we would like to have the norm of W as small as possible. Can you tell me why? Are you still there?
If we scale W and B, it will be still the same equation, but it will be a smaller margin, I guess, +1.
No, this is not the reason. Let's think a bit. Traian showed you when he talked about curve fitting about W. What happened when W was very, very high? Do you remember from that lecture? We had overfitting because if we leave the possibility of W to become as large as possible, then what we will end up will be having a spline that goes exactly through all the points, and therefore we have overfitting. So as a way to stop overfitting, we introduced regularization that imposed that the norm of W to be as small as possible, because in this way the error was partly consistent of the error from the data, and partly was influenced by this norm of W. And therefore, when this optimization problem had to be solved, we also considered the norm of W as part of the error, especially because we didn't want overfitting. So these two are the rules for the data that we have to respect, as to train the classifier to bring the correct classes for the data points. And this one is the rule because we don't want overfitting. Fortunately, to solve this, this is a convex problem, which means that there is only one optimum. And fortunately, we can solve it without learning rates or weight decay or early stopping or other means that are used in neural networks. With the help of an optimization program that is called quadratic programming, and that has been solved, has a complexity of n square, where n is the number of the training points. This means that if we have huge data sets, then n square will be too large, and therefore for these large data sets, we will end up doing approximate optimization. So we will not use quadratic programming. We will use, I don't know, gradient descent, probably. So that was about training. Once we have fit the classifier, so we established what will be W and B to have the equation WX plus B equal to 0. Now, if we have a new instance of X, we evaluate this W of W multiplied by X plus B. And if it's greater than 0, we say that is a positive class. If it's smaller than 0, we say that is a negative class. So this is the testing part of the SVM. Now, let's see how we identify these parameters, the weights and the bias. But before that, let's see why it is called support vector machine. As we increase the weight, the distance, the margin of the classifier, we will get over some data points. These data points are extremely important because these data points are the support vectors. This is how they are called. And they are extremely important because they establish what is both the offset and the orientation of the classifier. I told you 2 lectures ago that when we want to find a classifier, we need two pieces of information. First, we need the orientation of the classifier as to know how to put it in space. And the second thing that we need is the offset compared to the origin. Okay, so this distance, as to know where to place it. Now, if we have the support vectors, these 3 points, these 3 points will allow me to establish both the orientation of the classifier and the offset, and are the only points that are really important from the data set. Because if we remove any other points from here, then nothing will change. The classifier will be robust. So if we eliminate this point or whatever, the classifier will remain the same. Nothing will be changed. But if we remove, for example, this point, then the classifier might change both its position, so offset, and its orientation, because now this margin will be enlarged up to here, up to reaching this point, and also the orientation of the classifier might change a bit, might go a bit to the right, as to maximize the distance between this point and this point. Okay. Why do we use maximum margin? Well, there are a couple of reasons. First of all, it feels the safest, because if we make some small errors in the position or the offset of this classifier, by enlarging this margin, will give me some buffer, let's say. Okay, if the instance would be somewhere here, I will still consider it's greater than 0, so I will evaluate this point as being from the positive class. If the point is somewhere in here, then it will still be a negative class, a negative point, a point from the negative class. So if we have this area, this buffer around the classifier, we still have some area where, you know, we're not sure that the position or the orientation of the classifier is correct, but as we have this buffer, it might help us in the evaluation. So if we made a small error in the location of the boundary, this gives us the least chance of causing a misclassification. Moreover, it's robust, since the model is immune to any non-support vector removal, as I showed you on the previous slide. And in practice, it works very well. And now let's see how to estimate the margin. So this will be the boundary between the two classes. So it's the line that will give us wx plus b equal to 0. And now, if I want to evaluate the distance from point x from here to this line, do you remember how I can do this? To evaluate the distance from a point to I don't know, to anything, to a line, to a plane, to a whatever, to a surface. Do you remember how you can do that? This, I think, you have done when you've learned algebra in the space algebra, I don't know. So if you want to evaluate the distance from one point to a line, let's say, all you have to do is to input in the equation of the line. So in here, you have to put the value of the point that you need to evaluate. So these points get in here. So we have x multiplied by w plus b, and to divide it by the norm of w, so that to get a number of dimensions. So in order to evaluate the distance of x, the distance of x will be defined as the module of xw plus b divided by the norm of w, which is summation over all dimensions of this w squared, wi squared. Now, how can we define the margin? Well, we said that the margin will be the distance between the classifier and the closest points from the data point, the data set. Okay, so it will be the minimum of the distances between this classifier and all the other points. Okay, so it will be the margin, it will be the minimum of the distance. This is an error, this is not the argmax. Sorry, is not the argmin, is the minimum of the distances of x from the data set. So for all the data set points, out of the distance of x that we defined on the previous slide, and which looks like this. Okay. can you tell me if we put argmin, what it will give us? So this is the margin without arg. So it's only mean of the minimum of the distances over all the points from the dataset. But can you tell me what will give me argmin of d of x?
It will give us the point.
What point?
It will give us the point from the margin.
Okay, so if we have argmin, then it will return us the support vectors. Okay, so this is why I'm saying that is not correct argmin, but because argmin it's returning you the position of the points that are the support vectors. So this will return the support vectors. And to obtain the margin, all we need is the minimum of this distance. And the minimum of this distance is this formula. Now, SVM says that what we would like to have is to use the classifier that will maximize this margin. So what we will need next is to maximize the value of the margin. So we will be needing WMB that will maximize the margin, and this margin depends once of the data set that we have, so the points that we have for training, and on the other hand, it depends on WMB that need to be trained, so learned from the data set. And now, if we want to maximize the margin, it means that we will need to get the WMB that will increase this distance to the maximum. So it will be Rmax of the margin, meaning to be Rmax along Rmax depending on WMB from the minimum distance of all the points from the data set. So it's Rmax of the minimum of this value. So this is the definition of the SVM. This is what we would like to have to find out what are the WMB that will maximize the minimum distance of this form of all the points. And now let's see one more thing. If we have positive points that are somewhere placed around here, we will have for them wx plus b to be greater than 1 and the class y equal to 1. So the product, we will do something similar to what we did in the perceptron. We'll make the product of the class multiplied with the estimation of that point. And if those points are correctly classified, then this distance will be greater than 0. So for the positive class, we have y multiplied with wx plus b is greater than 0. And for the negative class, wx plus b is negative, and also the class is negative, is -1. So their product is greater than 0. So now, when we said that we would like to have the SVM, so we would like to have we would like to maximize the margin. This we will be maximizing it, but with respect to the data points that should be correctly classified. So we would like to have the maximization of the minimum distance, but in the same time, another rule that we have to respect, another restriction, is to correctly classify the points. So we need to have this wx plus b multiplied by y to be greater than 0 for all the points. So this is another restriction that we have for our problem. Okay, so these are the two things that we need in order to define the real problem that we are solving. So we need to find WMB that will maximize the minimum distance of the form from here, but subject to the product of yi multiplied by xi w plus b to be greater than 0. In other words, to not have errors, because if this product is greater than 0, it means that no matter the class of xi, this point is correctly classified. So these are the two things that we need to solve the SVM. These are the two restrictions. And now let's see another thing. You know, we said that for all the points from the dataset that are to the left of this yellow band, so of the margin, we said that the class is +1. For all the points that are to the right of this margin, we said that the class is -1. Okay, so it means that the points from class 1 have wx plus b greater than 1. Do you agree with that? So if we set this classifier to be y equal to 0, and if we have all the points having the class +1, it means that we can say that the left side of the margin, it will have the equation y equal to 1, because, you know, for all these points from the left, they should be in class y, and the distance should be greater than 1. And for all the points from the left, from the right, we should have y as being -1, and therefore all the points from here should be should have a distance that is greater than -1. So if we set these distances to be +1 here and -1 here, it means that for all the data points from the data set, we will have this rule. The module of the distance, or the distance from that point to the classifier, should be greater or equal to 1. Is equal to 1 if it's an SVM, if it's a support vector, so it is valid only for a couple of such points, and it's greater than 1 for all the other points. So the distance between the point and the classifier is greater or equal to 1 for all the data points. And therefore, if these distances are greater or equal to 1, what will be the minimum value of this? And for what points we will be having this distance? Still there? So if we want to minimize this distance, and we know that for all the points from the dataset, the value of this is greater or equal to 1, it means that the minimum value of this will be exactly 1. So basically, it means that what we would like to have is to identify the WMB that will maximize this value. This value that depends only on WMB, okay? Because we said that the distance from the points to the classifier is greater or equal to 1. It's equal to 1 only for the support vectors. And since the minimum of the distance is 1 for the support vectors, it means that this is replaced by 1. This doesn't depend on the dataset anymore, because we know that it's obtained, the value of 1 is obtained when we deal with the support vectors. So it means that the maximization of the margin is somehow simplified in this form. All we need is to find the WMB that will minimize, that will maximize 1 over the summation of W squared, which means to minimize the norm of W. Okay? So all we have to do for SVM is to minimize the norm of W with respect, and now since we consider that all the points from the data set are at a distance that is greater than 1, it means that we modify this because we said, okay, this is either plus or minus 1. This one should be greater than 1 if we have module. So it means that the product of yi multiplied by wxi plus b should be greater or equal to 1. So the modification is from here. Instead of having 0 as before, we with this modification, when we consider that all the points from the right of the margin should have the value at least -1, and all the points from the left of the margin should have the distance of at least 1. It means that the product of y multiplied by this distance, wx plus b, should be greater or equal to 1. It will be equal only for the support vectors. So the SVM problem now is reduced to finding w star and b star that will minimize this summation, and is somehow similar to what we did in the curve fitting when we applied regularization. We wanted to have the norm of W as small as possible, but also in the same time to have all the points correctly classified. So this is the main problem of keeping as low as possible the norm of W, but these are the constraints that are imposed by the data set. So yi multiplied by wx1 y1 multiplied by wx1 plus b to be greater or equal to 0 to 1, y2 multiplied by wx2 plus b to be greater than 1, and so on, yn multiplied by wxn plus b to be greater than 1. How can we solve this? With linear with quadratic programming. And to solve it with quadratic programming, we need to introduce some Lagrange multipliers. I won't insist on this. If you don't remember how to do it, you've learned in special maths. So if you don't remember how to do it, either you take a look on the Bishop book, and you'll see at the end, I think there is an annex of which is showing you how to use these Lagrange multipliers, or you take a look on the course from maths. Quadratic programming is a well-studied class of optimization algorithms to maximize quadratic function of some real value variables that are subject to some linear constraints. It's not something very easy to do. I mean, these algorithms were the results of some PhD programs. So it's very well studied, and it took a lot of time to come up with these algorithms. So you won't probably want to write quadratic programming solver on your own, but to use the existing ones. And this is how quadratic programming is defined. So what we need is to find the minimum value of u that will minimize the value of u that will minimize this this equation, where we have this quadratic criterion, where we have u transpose multiplied by r multiplied by u, and in the quadratic problem, in the quadratic formulation, we need some inequalities that are of this form, and also some equalities that are of this form. Again, there are algorithms for solving this quadratic programming, so it's better than gradient ascent, and it's easier to use this method to solve the problem if n is not too large, so n square being the complexity of the algorithm. To solve this problem, we need to define L of W, B, and A. So depends on the weights, on the value of the bias, and on the Lagrange multipliers. This is the weight that we would like to keep as low as possible. So this is the in here what we have. So we said that yn multiplied by wxm plus b should be greater or equal to 1. So it means that this part should be greater or equal to 0, okay? And this parameter will allow us to have some values that will not be equal to 0. So if this equation is equal to 0, then it means that in can be anything. If this is not equal to 0, then it means that in should be 0. So in are the Lagrange multiplier that will help me solve this equation. If we so this is the likelihood, right? If we derive the likelihood and set it to 0 in order to obtain W, what we'll get? We will get, you know, the derivation of this will cancel this 2, so we will have Wi's, and in here we will derive regarding to W. So this will disappear, and from here we will get summation over an, yn, xn. So this is what we get when we derive the loss and we set it to 0. And this is how we obtain the weights with the help of these Lagrange multipliers. And we also have the restriction that summation of an, yn to be equal to 0. So first we will need to find these parameters an, and then once we have set the values of an, we can compute the values of W as we have both y and xn. Now, we also define the dual form of the loss. We won't be using it. I'm not telling you how it's obtained. Again, if you want to find out, take a look in Bishop. The dual form, it's defined only in terms of the Lagrange multipliers, and is the summation of an minus half the summation of an, am, and qnm, where qnm is the product of yn, ym, xn, and xm. Basically, this will be a kernel. If you take a look, it compares the values of 2 points and multiply it with the value of the targets that these points will lead to. So this is the dual form, dual representation of the maximum margin problem. It has also these two restrictions, an to be greater or equal to 0, and summation of an, yn to be equal to 0. This is the same from here. And an should be greater or equal to 0 comes from Lagrange multipliers when they are introduced. This is one of the requests that an should be greater or equal to 0. Now, if you remember, to show you why it's this minus, if you remember, if the points were correctly classified, then this product would have been greater than 0. And if you remember from the perceptron, the error was with minus, because if the point is not correctly classified, it means that this product yn multiplied by wxn plus b is negative, and therefore in order to add it to the weights that we also have here, it means that we also need a minus in front of it, because if the point is incorrectly classified, this will be negative, -1 will still remain negative, and this should be added as an error to the weights, and this is why we have this minus here, because with this minus from the parentheses to get to the plus, so to increment the loss that we might have. Okay, so this is why we have this minus here. And again, if we derive the loss with respect to W and set it to 0, we will obtain this formula for W that will minimize the loss. Do you have questions? Okay. So we come back to the maximum margin problem. Why did we introduce the Lagrange multipliers? Because as you saw, when we want to use quadratic programming, we need to have this minimization of a quadratic term that is in here, and we also needed to have some inequalities. We had already this one, but we also needed some equalities that we didn't have. And this is why we had to introduce the Lagrange multipliers to give me these equations. AI multiplied by WI multiplied by WXI plus B minus 1 to be set to 0. So we needed these equalities, and this is why we needed, in fact, to introduce the Lagrange multipliers. The Lagrange multipliers also introduce some additional inequalities. As I told you, all the Lagrange multipliers should be positive or equal to 0. So now we have everything that we need to solve the quadratic problem. We have the quadratic criterion, we have some inequation, and we also have some equation. Is it clear? So the problem was that before we didn't have these equations, and they are required in the solving with the quadratic problem. Now, when we apply quadratic programming, we will obtain the values of AI. Based on the values of AI, we will obtain first W. Once we have W, we can identify the value of B. Once we have W and B, it means that we set up the classifier, and from then we can classify new instances of X and to assign Y of X to one of its one of these two classes, -1 or +1. Okay? Now, we get back to the problem. We need to find W and B that will minimize half the summation, half the norm of the W. With respect to these constraints, yi multiplied by wxi plus b to be greater or equal to 1. Fortunately, the problem is convex, so there is only a unique global minimum. There is also a unique minimizer, so the quadratic programming will only give you one solution for the weights and one solution for the b value. These two, in fact, the weights will be a vector of values. So these values together will take you to the minimum value of the loss and will help us build a solution of the SVM. However, if the data is not linearly separable, this is not solvable. So quadratic programming will not return anything if the data is not linearly separable. And this quadratic programming is very efficient computationally. It includes modern constraint optimization engines and may handle thousands of constraints and training instances. So again, it's a very efficient algorithm, but you probably don't want to write one of these algorithms on your own. It's easier to use the algorithms that are already implemented. So if the data was linearly classifiable, this is the solution. I showed you how. We need to impose the fact that all the points should be correctly classified. So the product of yi multiplied by wxi plus b to be greater than 1. And we also want to minimize the weights of w as to avoid overfitting. And to solve it, we need some equalities. These equalities are introduced by the introduction of Lagrange multipliers, and based on that equalities, the problem is solvable. But however, it's solvable only if the data is linearly classifiable. Most of the time, the data is not linearly classifiable. So let's suppose that we have one uh, one situation similar to the one described on this slide, okay, where we have either some errors in the data, or simply the data is not linearly classifiable. What can we do? Because in this case is the quadratic programming with the normal with the classical definition will return nothing. How can we solve this problem? I'm listening for any suggestion from your side. How we should do this? Any idea?
We try to increase the dimensions and see if they are linearly separable in a higher dimension.
This is a very good solution. We will be talking about it a bit later. Yes, it's one of the options that we have to use a kernel in order to get in a higher space where the data becomes linearly separable. But for the moment, so we'll get there. It's a good solution, but we'll get there a bit later. Now we want to stay in the features, in the space of the features that we have. So not increase the dimensions, the number of features, not using any kernel or something. So we need to stay in this space. How can we solve this? You know, this solution we're getting in a higher dimensional space where the data set might become linearly classifiable is a good approach, but it doesn't guarantee that the data will become linearly separable. I mean, we get to a higher space in the hope that the data set will become linearly separable, but we might not get there and we still have to solve the problem. So if this is happening, then actually what is happening is to return to this issue. So we cannot simply say, okay, we'll go in a higher dimensional and there the data set will be linearly separable, because this is not actually true. So we still need to solve this problem where we have some either errors or, I don't know, simply the data is not linearly separable. Once we will find the solution for this, we'll be able to extrapolate and to say the same in the space that is obtained after applying some kernels. Yes, you are saying something.
Yes, I remember there was a theorem that said the more the more you increase the number of dimensions, in which you separate data, the sparser it gets, and the sparser it gets, it is more likely to become linearly separable.
It's
and
true.
It is a statistical formula, I think, for how the sparser it gets, the more likely it is to become linearly separable. But I don't remember it.
It is true what you're saying, but again, it is more likely to become linearly separable. But this more likely, it remains more likely, it's not guaranteed. And for example, the example from here, it has only some outliers. Okay, these are errors. As the data seems to be like, these are likely to be outliers. And if you have outliers or errors in the measurements, you can go in any number of dimensions that you like. They will remain some errors, and they will be placed in other places than where you would like to be. So, for example, this one either should be colored or should be placed somewhere around here. But due to some errors that you'll see that in when you get to work with these data sets, you'll see that there is absolutely no data set that have that has no errors. So you'll have to deal with it. You can go in a space where these points will be I don't know, separable by a linear classifier, but you know, to get there, you will actually achieve overfitting, in fact, because you simply increase the number of dimensions. By increasing the number of dimensions, you introduce new parameters, and these parameters will fit to the data that you'll provide. And if these are errors, then you will also fit the errors instead of simply finding a classifier and say, okay, these are some errors, we'll simply ignore them, but the classifier should stay like this. Does it make sense what I'm saying?
Yes, it does. So we should minimize, if we try the multidimensional method, we should try to minimize the sparsity of the data while maximizing the linear separability, something like that.
Yes, it is true, but what you're saying is minimizing the errors, basically, because uh, you would like to minimize the sparsity of the data while maximizing the separability, linear separability. But these again are not guaranteed to lead you to some spaces, some dimensions, some I don't know, some new space where the data becomes linearly separable.
Yes, it will have error. I understood that.
Yes. So we'll have to cope with the errors, and once we learn how to do it in the original plane, of course, when we get to a higher dimensional space, uh, these errors will be softer. Let's say will attenuate. Okay. So first, let's see how can we redefine the problem so that to deal with these errors that we have. How can we define the loss to also consider these points that are not correctly classified? What should be minimized? So we already know that for the problem of from the problem where the data is linearly separable, we need to minimize W with respect to the product yi multiplied by wxi plus bi plus b, sorry, to be greater or equal to 1. Now, what needs to be changed in order to also consider these errors? how can we modify what is being minimized so that to consider also these points. Can you say, for example, okay, let's minimize the norm of W while also minimizing the number of errors? Can we define it like this? Does it make sense to be defined like this? So try to separate the data set, but in the same time try to minimize the errors that we might have. So find the minimum W while minimizing the number of the training set errors. This is one of the possibilities, but there is a problem. We need to minimize in the same time two different things. First of all, we need to minimize the norm of W, and in the second term, we need to minimize the number of training set errors. And in here, since we need to minimize both of them, we will get to 0, because this is the way to satisfy both of them. So we need to find a way that will give enough. I don't know. We need to say, okay, which one of these two is more important for us? To minimize the norm of W, or to minimize the number of training errors? Because they will not. Somehow they are opposing one to each other. If we want to find the minimum W, it will be, I don't know, something like this, for example. If we need to minimize the number of training set errors, it should be something like a classifier like this, that basically overfits, okay? And when you overfit, the norm of W goes very high, so you cannot satisfy the first part, minimize the norm of W. If you get to this form, then the number of errors will get high, so you cannot satisfy the second part of the problem. So in order to use this evaluation, this I don't know, definition of the classifier, you need first to set a trade-off parameter, this value of C, that will show you how much importance you give to minimizing this compared to how much importance you give to minimizing this. And this value of C will show me it's a trade-off parameter that will help me in this task. However, the value of C is impossible to be evaluated automatically. So it should be guessed by the programmer. Okay. Moreover, there is another problem. If we use this definition, W, the norm of W plus C multiplied by the number of training errors, this cannot be expressed as a quadratic programming. So we need to find out a different way to solve it. Different way meaning probably gradient descent. And if we use gradient descent, the solving may be slow. And we also might have the issue of having some local minima that will stop us from getting to the global minima. So we are not sure that we will end up this optimization problem in the right spot. Also, there is another problem. If we minimize the number of training errors, we cannot say if that error was a disastrous error or it was a near miss. I mean, the error, how can I translate this? If I move a bit the classifier, will these errors disappear? Because if so, it means that they are near misses and they should be differently considered compared to disastrous errors that will remain there no matter what I do with the classifier. So we'll need to change this this estimation, this definition, as to also consider how much is the error of that point. And how can you define this? You can define it by the distance between the point and the position, the current position of the classifier. So we will need to find a way of defining the distance of error from the points from the position where they are to the point where they should be in order to be correctly classified. And if we define this, then the SVM problem will be changed like this. We will need to identify the W and B star that will minimize the summation between the norm plus C, the parameter that I told you that needs to be introduced by the programmer, and the summation of these are the errors, XCJs, let's say. And this minimization should be with respect to the fact that all the points should be greater or equal. So y1 multiplied by wx1 plus b should be greater or equal to 1 minus x1. For y2 should be greater or equal to 1 minus x2. And finally, yn should be greater or equal to 1 minus xn, where all these xi should be greater or equal to 0. So let's suppose this is the line with 0, okay? This is a minus 1. So how far it is from the points, from the plane where it should have been? Well, we compute this distance that is defined as x1, and this distance is positive because it's a distance. And if we consider 1 minus this distance, it means where it should have been placed in order to be correctly classified, because this is 1 from here to here, as you saw in the previous slides. And if this distance, of course, is greater than 1, so this value is smaller than 0, and this is where it should have been placed. Xi are called slack variables, and the value C, it's a balance, it's a trade-off between the margin and the classification errors. However, again, this is a parameter that needs to be decided by the programmer. It cannot be inferred automatically. So the definition for the noisy data, it should follow this description. It's the minimization of the norm plus the trade-off parameter C multiplied by the Xi's, the slack variables, with respect to this inequation, yi multiplied by double xi plus b to be greater or equal to 1 minus xi, and xi's should be greater or equal to 0. This problem, after introducing the Lagrange multipliers, will be solved with quadratic programming. The algorithm will try to maintain xi's to 0, and in the same time they will try to maximize the margin. However, you should notice that the algorithm doesn't minimize the number of misclassification, which is an NP-complete problem, but the sum of distances from the margin hyperplanes to the position of the errors. To show the fact that the slack variables should be positive, there are some formulations that use xi squared instead of xi, because you know the squared value is always positive. If we increase the value of c, so if we put a lot of weights on the errors, on the xi's, as c increases, we obtain a formulation that is closer to the initial formulation of the problem, which is called hard margin solution. This solution is called soft margin SVM. And to see the difference between them, we will see in the morning on the next slide. However, in this formulation for soft margin problem, we have the issue of finding the value of c. We don't know how to determine this value of c. The value of c should depend on the data set, because it's a trade-off of the data set. It's a trade-off between the number of errors that I may find reasonable for our data set compared to how well I want the data set to be classified. And again, we'll see in a few moments, we'll see what is the difference when applying soft margin SVM or hard margin SVM. We will see in a moment. Now, first, let's see equivalent quadratic programming. I showed you this is the dual form of the quadratic programming. Oh, sorry, dual form of the SVM, of the maximizing the margin. And I told you that we need to maximize alpha k minus half of alpha k multiplied by alpha L multiplied by QKL, which QKL is the product of YK, YL, XK, and XL. And I told you that this, in fact, will be a kernel, but we'll see this in the end. Now, for the soft margin problem, we need to impose the value of C. And if we solve, if we impose the value of C and we solve this equation, this equivalent quadratic programming, then we will see that the values of alpha k's will be smaller, strictly smaller than C and greater than 0 for the support vectors. So for the points that are important, will be set to 0 for the data that is correctly classified. So I don't care about this data. I'm only interested to be correctly classified. But then again, once we know that the data is correctly classified, you saw that all we need is the support vectors. The other data may be discarded. And we will see that the points that are incorrectly classified will have AK equal to C. These points, again, I know that are incorrectly classified, but I'm not interested in them when we compute the position of the classifier. So when we compute W, we saw that the value of W was given by AK, YK, XK, but only for the support vectors. So once we know that we impose the value of C, we apply quadratic programming from the quadratic programming, we'll get this value AK. For all the values that are greater than 0 and smaller than the threshold that we imposed, it means that those are the support vectors, and those are the weights, the only points that will influence the weights of the classifier. Because you see in here we will need YK, the classification of the point, and XK, the point that is being classified. And this is the summation is done only on the support vectors. So only on those points having AK greater than 0 but smaller, strictly smaller than C. So the points with AK equal to 0 will not have any influence, because AK equal to 0, it means that the point will not, this product will be 0, so will not influence in any how the classifier. But we will also ignore the points having AK equal to C, because we know that those points are the ones that are incorrectly classified. So we'll actually use only to compute the weights of the classifier. We will only need the support vectors. So those points that will have associated AK values that are strictly smaller than C and strictly higher than 0. Now, here is the difference between the soft and hard margin SVM. In the left image, we have a soft margin SVM, and you see that we permit the existence of this point that is incorrectly classified with the help of a slack variable. But if we use that, you see how large is this margin. On the same data set, if we use a hard margin SVM, it means that even though this might be an outlier, we are not allowed to ignore it, let's say, and therefore we will lead. This will lead to a different positioning and orientation of the classifier that would lead to a much smaller margin, and therefore I don't know. I would rather have something like this than something like this. I feel more confident if the margin is larger than what's happening in here. More important, soft margin SVM always have a solution. So the quadratic programming defined considering these slack variables will provide a solution. Is more robust to outliers and will generate smoother surfaces in case of the non-linear classification. But on the same time, it will require to identify the value of C that we don't know how to evaluate. On the other hand, higher margin SVM doesn't require to guess the value of C at all, but will generate this kind of classifiers that are not so, I don't know, robust. Okay? Are you still with me? Is there anything that you didn't understand? Do you have any questions? Can we continue? Can you still hear me?
Yes, yes.
Yes.
Okay. So everything is clear up to now.
Yeah, I think so.
Okay. Now, I told you that from the quadratic programming, we get the values of AK, and we saw on the previous slide that based on the values of AK, we get the values of W. Now, once we have the value of W, so these W stars will be obtained from the quadratic programming. But in order to finalize SVM, so to solve the problem and to find the classifier, this W will give us only the orientation. We also need the value of B. However, B will be the value that will consider will depend only on B and the slack variables, and with B the position of the classifier, so this B will be only the offset. Once we have double, we know the orientation, but having this orientation, you know, we can put it in here, we can put it in here, we can put it in here, and this orientation stays the same, but the offset is different. Okay, so from the origin you make the perpendicular, and this is the distance, the offset. This is B that we need to evaluate, and the value of B will depend also on the slack variables, because we need to minimize the summation of these slack variables from the soft margin SVM definition. However, this is a linear programming problem, so it's solvable in O of n. It's fast. Once we have fixed the orientation, all we need to be is to put it higher or lower in the space, and we will. This is done basically depending on the slack variables. So this should not pose any more problems from now on. It's easy to compute. Okay, so that was what happened if we had 1D and the classification was clear. But now we go to the solution that was presented earlier by your colleague, who said, okay, if we cannot classify correctly, if the data is not correctly classifiable, then we go to a higher space. For example, we may use polynomial basis function that will lead us to another space. So use a function, a basis function to map the original space into a different space where the data set becomes linearly separable. So this is what's happening. We use such a basis function that in this case is polynomial, but we could use a radial basis function or a sigmoid, or I don't know, different exponential, and we will get to a different space. So again, these are some examples of basis functions that may be used: polynomial, radial basis function, sigmoid, and so on. So this will lead us to obtaining a linearly separable data set if we get to a higher dimensional space, and if we don't have errors, as I told you earlier. But there is one more thing that we should know. Suppose that we have a basis function that looks like this. You know, we have m dimensions for the basis function, and let's suppose that we have these terms. Okay, we have a 1, and then this is a constant. Then we have some linear terms. We have some pure quadratic terms where we have only 1 dimension squared, and we have some quadratic cross terms. Now, if we want to multiply two basis functions, so if we want to have phi of x multiplied by phi of y, because you saw that in the dual definition, we had something like we had x1 multiplied by x2 multiplied by y1 multiplied by y2. And now if we are doing this change, when we define this basis function, it means that when we compute that function, we don't have x1 and x2, but we have phi of x1 multiplied by phi of x2 multiplied by y1 multiplied by y2. So we will need to do this computation, y of x multiplied by y of, phi of x multiplied by phi of x1 multiplied by phi of x2. So we need to do this, this product. How many operations we will have when we want to compute this? Well, let's see how this will be a dot product. So we will have a number of of multiplications equal to the number of terms in this basis function. So let's see how many terms we have in here. We have one constant. We have m linear terms. So this is 1. This is m. This is also m. How many terms are in here? Can you tell me how many cross terms, quadratic cross terms, do we have?
M times M minus 1.
Over 2. So it's combination of m taken 2. So it's m minus 1 divided by 2. So
right, yeah.
If we compute the sum of all the terms, okay, it's 4m plus 2 plus m squared minus m over 2. So it will be m squared plus 3m plus 2 over 2. This is m plus 1 times m plus 2 over 2. And this is the number of terms from the basis function x. And we can, if we have m plus 1 multiplied by m plus 2, we can estimate it as having m squared over 2 such terms, which means that when we want to make this computation, phi of x1 multiplied by phi of x2, we will have an m squared over 2 operations that we will need to have, roughly, so approximate. Now, we have some SQRT of 2. We will see in a moment what's the role of them. They are very important. It's very nice that we can have it there. You'll see in a moment why they are used there. They're not influencing because, again, as one of your colleagues said, by multiplying with the constant any value from any dimension, nothing will be changed. So it's important that you can have them there, and we will see in a moment why we have them there. So let's do the math. If we want to compute phi of x1 multiplied by phi of x2, we change x1 with a and x2 with b because it's easier to see. So when we compute the product, we will have 1 plus, these are again dot products, so the multiplication are done like this. So SQRT of 2 multiplied by SQRT of 2 will give you the value of 2. A1 multiplied by B1, we will have for all these terms, this situation. So we will have the summation over all dimensions of 2 AI BI. These are pure quadratic terms that are multiplied. So we will have AI squared BI squared. And these are again cross values. So we will have terms that have all the A's and all the B's. So we will have AI, AJ, BI, BJ, and the two from these terms. And now to compute this, we said that we need m squared over 2 operations. Now, we will try to see if we start from this value, what we will obtain. So first, we will try to make the product between A and B, and then to square it. So instead of doing phi of A, so to get the basis function of A, to get the basis function of B, and then to multiply these two basis function, we would like to have first to have A and B. We add this this one, and to see what's happening there. So if we have AB plus 1 squared, it's the formula that you know, AB squared plus 2AB plus 1. A and B are multidimensional, so we will have summation over AI BI squared plus 2 summation of AI BI plus 1. However, in here, when we multiply this, we will have summation of A from this part. So for this part, we will have I. For the second part, we will have a J. And this summation, so this is this one, this summation can be, you know, if we have a matrix, let's say, then we have the first diagonal where I equal to J, and then these terms will be symmetric. Okay, we will have the same value. Does it make sense? Because if I has a value M, let's say, J has a value N, is the same. So this situation is the same as having I equal to N and G equal to M. Okay, because we will have A M B M A N B N for the first situation, and then we will have A N B N A M B M for the second. So this is why I'm telling you that the positioning from this we have a triangular data that is symmetric. So what we have in here, we will have also in here. So we can separate this this summation in two terms. The terms from the first diagonal. Okay, so this that will be AI BI squared. And since this data is the same with this data, it means that we have 2 times this situation where a triangular. So we will have I from 1 to M and J from I plus 1 to M. And if you take a look on this formulation, this is this. This is this one. This one is the one from here, and the unit is from here. Now, to compute this, we only need M operation, because to multiply A and B, they will be M dimensional. So the product will be will have the value of M, and therefore instead of having M squared over 2 operations to compute this one, we can use this trick to do the same computation in O of M time. Okay. So we can first of all to get rid of the problem with non-linear separability, we will have to go using the basis function. So the main change is that instead of using xk multiplied by xl, we will use in fact phi of xk multiplied by phi of xl. And this is what's happening in here. Again, we will have to impose the value of C, and all the points that will have AK smaller, strictly smaller than C, and strictly higher than 0, we will give us the support vectors, and will be the only ones that will influence the positioning of the classifier. But when we compute the W, instead of xk, again, we will have to use phi of xk. Afterwards, once we set the value of W, the value of B can be identified from this formula, yk multiplied by 1 minus ck minus xkwk, where the value of k is argmax of ak. So the maximum value, this c. Once we have the value of W and B, to classify a new point, we get first from x to phi of x. The value of W and B were computed in here. So we can compute this product, we take the sign, and we decide whether it's a positive or negative plus. But we can still do another thing, because you saw when Traian taught you that the product of basis functions can be defined as a kernel, and therefore another thing that we can do, it's called a kernel trick, is that instead of using phi of xk multiplied by phi of xl, we simply say that we build a kernel that is computed based on xk and xl, and we use this kernel to define our dual formulation of the problem. Once we have this dual formulation, we can compute AK. Based on AK, we can identify the values of W and B. And now, when we need to classify a new data point, all we need to do is to find the kernel between W and X, to add the value of B, compute the sign, and boom, it's done. All we need to do is to classify it in positive or negative class. Okay, so the most important change was to go from the product of the basis function to the kernel function that involves the values of xk and xl. And that's basically the end of what we can do with these SVMs. There are still some pros and cons to these kernel tricks. The pro is the fact that we are introducing nonlinearity into the model and this computational chip. You saw that we can solve in constant time in O of m, no matter how large is this kernel. So I showed you that we can do we can use a quadratic kernel, but you can use AB plus 1 to other values. So I showed you a quadratic kernel, but you shouldn't be limited to this value. You can use higher values, higher dimensions, 3, 4, 5, and so on. So no matter how many dimensions you have here, you can still do the product in the initial space with O of m, and then to go to the complexity that you desire based on the complexity that you choose for your kernel, for your basis function. So this is nice to have, no matter how large we will use the power of the kernel of the polynomial basis function that we are using. We still compute the product of two basis functions of the kernel in constant time in O of m. Well, when I say constant, it means that it won't change based on the power of the polynomial function. It's not constant, is O of m. Okay, so it depends on the number of dimensions, but still is computational cheap. Con to the kernel tricks is still have potential overfitting problems that I outlined when when there was the discussion of going from the initial space to another space where the data will become separated, linearly separable, and I told you that if we have errors, so not the fact that the data is not linearly classifiable is not due to the structure of the data, but is due to some errors. Then by going to a higher dimensional space, all we will end up doing will be to fit the errors. So still we have some overfitting problems. This is a way of how the polynomial of degree 2 will look like. So if you use a kernel that will be like this, xij plus 1 to the square will look like this, and these are the support vectors for both classes. This is how a kernel that is radial or Gaussian will look like. So this is the kernel that is used, and again we have a couple of support vectors for each surface. Now, all we talked up until now was about two classes. So we had a binary classification. The problem is, how can we do a multi-class classification, because this is not supported by SVM. As I showed you, SVM can only handle two class outputs, so a categorical output with arity 2. So if we want to do multi-class classification, we can try to apply the method, the options that I told you in my last presentation, either to use one versus all or one versus one type of classifier, and then to apply different heuristics to make the final decision. So one solution is one versus all, train n binary classifiers, and each of the classifiers should say that a point is in a class or not, and then once you evaluated a new point using all these classifiers to define the predicted class as being the one that is most confident, so the one that will give you the highest value, the farthest in the positive region. You can use 1 versus 1, so you'll have n multiplied by n minus 1 over two classifiers, each discriminating between a set of two classes, and then you will need several strategies for selecting the final classification. There is also generalization of SVM that is available for multiple categories. So to try to truly use multi-class SVM, but is more complex, and it will require much more time to fit. There are also other types of kernels. There are kernels for regression. There are kernels. There are other types of SVMs. There are SVMs for regression, SVMs for clustering, micro SVMs that will maximize the margin while bounding the number of margin errors. So it's somehow in between soft margin and hard margin SVM. So we still try to maximize the margin. We still accept some errors, but we limit the maximum number of errors that are, I don't know, accepted for the problem. So again, it's something in between hard and soft margin SVM. Leave one out, minimize the bound of leave one out error. SVMs that will consider difference in cost of means classification remember when we talked about patients with cancer, and I told you that there is a different cost of having false positive or false negative, and there are some SVM formulation that take in consideration this difference in cost. There are kernels for sequences of strings and are very successful. And so on. There are a lot of other methods for kernels. SVMs can be used in recursive feature elimination. For example, you can train a linear SVM, see what variables have the lowest weights, because those variables will be the one affecting the least the classification, and therefore you can remove those, and then retrain the SVM only with the remaining variables, and repeat this procedure until you have reached a number of variables that is satisfiable. Is very successful. There are some other formulation where minimizing the number of variables is also folded into the optimization problem. So instead of minimizing the number of the weights, so the W multiplied by W squared, so the norm of the weights plus C multiplied with the 1 minus Ci values. The minimization will also try to consider the number of variables. So it's the number of variables it's placed in there, and therefore some of the variables will have will have zero coefficients and will disappear from the final estimator. There are similar algorithms for nonlinear SVMs, and are some efficient methods for variable selections. We will also see in my next lecture PCA, which is a different alternative for variable selections. In terms of performance, SVM worked well in practice. You know, now we all talk about deep learning, which I told you it's a deep learning method is nothing else than a network of different perceptrons placed in different positions and so on. And as I told you, an SVM is only a smarter perceptron. What we expect to see in the future is that we will see some networks of SVMs, as we saw multi-layer perceptrons evolving in this deep learning methodology with a lot of hype around it. We expect that in the future we will see something related to SVMs, as SVMs are stronger than simple perceptrons, and there might be some changes that may be done to SVMs so that to lead to such deep networks of SVMs. So this is what I expect to see in the future. However, their performance as individual SVMs work good in practice. The user must choose the kernel function that he wants for the dataset and its parameters, and the rest is automatic. It can be expensive in time and space for big datasets, because you saw that quadratic programming has a complexity that depends on the square of the number of training cases. Also, is not very friendly in terms of storing, because we need to store all the support vectors. Is not as bad as having to store all the data set, because once you found out what are the support vectors, it's enough to store these support vectors, and the rest of data may be discarded. SVMs are good if you have no idea about what structure to impose on the task. And the kernel tree can also be used to do PCA in a much higher dimensional space, giving a non-linear version of PCA in the original space. Again, we will be talking of PCA in my next lecture, so in 2 weeks from now. We talk about what they can do now. We'll talk about what are the problems. SVM use each training case, but the programmer need to define the feature to be used. So actually the user is responsible to design the features, and it will depend a lot on his experience or her experience in designing these features, the performance of the SVM, because the SVM only do feature selections. If the features are not well designed, then it will simply choose from some bad such features, and it won't output good results. So actually SVMs are simply learning how to weigh different features that are designed by the user to optimize the problem. As I told you, SVM is a very clear way to train a standard perceptrons, but it still remains a perceptron. So everything that a perceptron cannot do cannot also be done by SVM. For example, the XOR cannot be solved by an SVM. Some references, and this will be all for today. If you have questions, I would like to hear them and try to answer.
Yeah, sorry, I would have a question.
Please.
It's regarding the first part of the course. I didn't quite understand why, if we have big values of W, then we have overfitting.
Well, to find out about this, you should take a look on the second lecture, because Traian showed you that when you have, let me try to, in fact, I think I could open the presentation. 1 second. I'm searching for Traian's presentation. To show you what's happening when you have overfitting, and you'll see. Come on. I'm sharing right now. Can you see the PDF?
Yeah, I can see it.
So Traian showed you that when the complexity of the curve is increased, then you'll get to a spline like this, and the values of W's, as you can see, will increase. if you have something like this, it's clear that you're not having a classifier anymore. You have a spline, as you can see in here. M equal to, well, now you have overfitting for this slide. You still have underfitting.
Yeah.
Underfitting. Yeah, underfitting. Here you have underfitting. Again, it's still underfitting. Here you have a good estimator. But when you get here, you have a spline that will get exactly through all the points, okay? And if we take a look on the parameters in each of these cases, you'll see when you have underfitting, you have very small values. You see 0.19, 0.82, and so on. When you have a good estimator, you have a decent values for the parameters for W's. But when you have overfitting, you have a lot of a very huge number here. And this is why you would like to have this regularization that imposes in the error to also have to also consider the weights, because once you intend to keep the weights low, they won't be able to fit to a spline, and therefore you avoid this overfitting. Okay.
Yeah. Okay. It's clearer now.
Okay.
Yeah. Thank you. Thank you very much.
You're welcome. Some other questions?
Me? I was wondering if we have outliers that are so bad that maybe, I don't know, we have to classify, let's say the vast majority of blue points are towards numbers, the vast majority of red points are towards positive numbers, but there are some and around 0 there is some noise, but
okay,
let's say red points way over to the negative billions. Those outliers are going to badly influence my estimator and my classifier. And I was wondering, maybe we can use some ransack or some algorithm to get rid of the outliers altogether.
You can do that. There are algorithms that will allow you to remove some of outliers, and most of the time it is highly recommended to first take a look of your data, because there might be situations where you would need to clean the data before doing any training. What you will want during a training is to fit the data, not the errors. And therefore, if you can do anything to remove these errors prior to learning, it's an excellent idea. So most of the time, this is what I would do. First, look at the data, eliminate the outliers if I can, and only afterwards try to fit the data. Okay? So if you can find any algorithms, any good algorithms, or any heuristics that you can use to clean the data, then do it. And only after the data is cleaned, the remaining data should be used as training. Okay?
Okay.
Any other questions? If not, thank you for attention, and see you next time with Traian. And in 2 weeks, I'll present you another class. Bye bye. Have a nice evening.
Thank you. Bye bye.
Thank you.
Bye.
Bye bye.